Yeah, I think I'm all set.
Oh, this is them.
Nah.
In case they won't see.
Try to do my best.
It's live.
Live on.
Speak to the microphone, okay? That's good. Good morning. Today we have Mathieu Roskosz as our visitor, and we should welcome him. Mathieu was a postdoc here years ago. Prior to that, I guess he got a PhD out of Nancy, was it? Yeah. Then he was a postdoc here for a couple of years in the mid-2000s. Worked with me, actually, as a matter of fact. Before returning to France, went to Lille, where he spent 8, 9 years.
8 years, yeah.
8 years before moving to a very nice spot called the Museum of Natural History in Paris, where he currently is a full professor. So Mathieu is going to talk about, as obviously, structural controls on R and thin isotope variations in planetary bodies. Hopefully you'll learn something. I'm sure you'll learn something.
Thank you, Bjorn.
I will learn something anyway. As you most of you know, I don't know anything about isotopes. So I'll leave it to you. Thank you.
Thanks. Yeah, can you hear me? Yeah, thanks. Okay, so thank you, Bjorn. Thank you for the introduction and the invitation. I'm honored to be here, first because I will show you some studies that I initiated here when I was a postdoc with Bjorn. We started to work with Tim Mock, Mary Horan, Connell, Eric Horry was also involved, Faye. And I remember the first day I came here, I arrived here, and I got this fellowship to work on this iron isotope partitioning. And I entered in Bjorn's office and said, okay, so it's nice, you have your fellowship, but I'm not quite sure about your project. So maybe you should think about doing side projects. So we've been doing some nice studies about nitrogen speciation in silicate melts. And I've also started this study. And it turns out that the two ideas were good. And so today I will focus on iron isotopes. As you can see, there's a painting here. This painting has been painted by a very famous Russian, French painter. His name is Serge Polyakov. And for those who knows a little bit about iron isotopes and this spectroscopy, Polyakov is someone very important for this domain. So to start with some very basic slides, the idea of understanding the way the planetary accretion, differentiation, and the core formation works is basically focused on understanding how you move from this messy rock that we call a chondrite to this kind of planetary bodies. So this is an SEM picture of the Semarcona primitive chondrite. And here you can see at the very small scale, iron-rich silicates, iron-poor silicates. You have phyllosilicates here. You have organics, sulfides, rims, and different kind of metallic alloys. And everything is obviously in thermodynamic disequilibrium. And in the end, you end up with well-sorted planetary bodies with like on the Earth, the iron alloys at the bottom of the Earth, at the center of the Earth, and then a silicate layer and the hydrosphere and atmosphere at the top of this. So how do you understand, how can we understand the different processes and the thermodynamics that control this kind of differentiation? So another very trivial slide to begin with. So this early differentiation, because it occurred very early in planets and in planetesimals, involved the physical separation of silicates and iron-rich alloys. And this process required high temperature in order to melt the metal and to segregate the metal into one phase. And this heat was supplied by the radioactive decay of aluminum-26 and iron-60, and also later by the high energy impacts. What is important is that because of this core formation, the Earth's mantle is depleted in siderophile, which is the iron-loving elements. And this has very distinctive signatures that we can observe at the surface of the Earth. But differentiation is not restricted to this metal silicate segregation. It also implies the formation of the oceanic crust, the subduction and the onset of the plate tectonic, the melting of the mantle wedge, the formation of deep magmas. And so all these kind of processes that for some of us may appear as a supersurface processes are also very important in order to understand how you make the different layers of the Earth. Another slide, just to settle a little bit the studies that I'm going to present you. This is a very famous figure where the abundances of the elements normalized to Ci, chondrite and magnesium are plotted against the 50% condensation temperature at one particular pressure, 10 to minus 4, and in a particular gas, which is hydrogen. So this is just one figure. This is not the only presentation that we can have on this type. What is interesting here is that there is a difference between the lithophile elements that align the blue along these blue trends. The first ones here are volatile, are lithophiles and refractory. These ones are volatiles, and so this trend is related to the volatilization of these elements. All these elements that you can see here in red and black are iron-loving elements, and as you can see, they are depleted as compared to the chondritic abundances because they have been scavenged into the core forming materials. The two elements that I will focus on today are iron, which is a siderophile element, but not that siderophile actually, and tin. So tin is also siderophile, and it's at the end of the volatility trend. So it's both a volatile element and a siderophile element. So these are the two elements that I will focus on, and I will tell you a little bit later why I'm focused on these two guys and not on silicon or other usual suspects. So now let's move a little bit further into the phenomenology of the iron and tin isotopes. So this time I will focus on the results collected by analytical geochemists. And so the observable that they have in hands are rocks formed at the divergent plate boundaries, which as morbs, essentially. What happens in the continental crust here around the subducted slab. They also have samples from hotspots and also at the convergent plate boundary. So what happens when we look at the isotopic signature of these kind of rocks? Well, at the divergent plate boundaries, which are here, the first important things that has been revealed in the past 10 years, 20 years now, is the fact that morbs appear to be enriched in heavy iron isotopes, the 56 against 54. They are enriched in heavy isotopes as compared to peridotites. There's still a little bit of controversy about this figure because what we call peridotite is always a bit tricky. Because most of the peridotites have been metasomatized, which means that the isotopic signature of its rocks may have been modified. But if we take the most pristine or the less metasomatized rocks, it appears that statistically the peridotites are close to this zero. I will define this zero a bit later. So this kind of results tells us that maybe this distinctive signature of MORBS is related to the partial melting of the upper mantle. There are also some signatures, crystal signatures. As you can see here is the isotopic signature of iron as a function of the silicon content of the host rock. And when you increase into the silicic, granitoids kind of rock, the isotopic signature of iron increases and the rocks becomes much heavier. So is it a signature of fluidic solution, or is it related to something else? We don't know, or at least without a strong theoretical or experimental background, it's quite complicated to interpret this kind of feature. Now, in terms of planetary signature, so you can see here the peridotite and the MORBS and OIBs with the shift toward the heavy isotopes for these magmas. And if we compare this data to the chondrites and to other planetary bodies like Vesta, Mars, you can see that actually this signature of MORBS seems to be pretty unique. Actually, it's not. There are some meteorites that exhibit some heavy iron isotope signatures like anhydrites. But most of the rocks we have access, extraterrestrial rocks that we have access to, have data close to zero. And so the zero here is maybe defined as the chondritic composition. So it appears that the modern peridotites may be chondritic, but the MORBS and the OIBs are not. So why are terrestrial magmas enriched in heavy isotopes? What could be the processes or the thermodynamical parameters that control this, and why does it make the Earth unique in this respect? There are two main reasons. The first one, we can argue that actually the Earth is, or at least the surface of the Earth is more oxidized than most of the planetary bodies that we probe these days, including Mars and Vesta. And so maybe the signature that we observe with iron isotopes is a signature of the oxidation state of the Earth. That's one interesting hypothesis. The second one is that actually the Earth is the biggest planetary body that we, the largest planetary body that we probe, we have samples from. And so maybe what we observe is an effect of pressure, because the pressure is very, very high at the core mantle boundary for the Earth. And so maybe something's going on with isotopes that we can trace and that tells us something about the pressure effects and the way the planet are created. Moving to tin, so tin is much less conventional geochemical system. We don't have a lot of data. The first data were published in the 2 or 3 last years. These are the data collected by the group Fred Moignet in IPGP. And what you can see here is that there are some pretty large variation of the isotopic composition of tin as a function of chemical parameters. Could be potassium content, silicon content here on this study. And they propose a sequence of differentiation of the magmas that is associated to a pretty strong fractionation of tin isotopes. So it appears that tin may be also a good tracer of magma differentiation. And in terms of cosmochemical signatures, there are also interesting data that have been published by the group by Caroline Fitoussi and Bernard Bourdon in Lyon. The first data set is related to ordinary chondrites and carbonaceous chondrites. And as you can see, in ordinary chondrites, there is a lot of scattering. This is probably due to vaporization because tin is volatile. But the interpretation of this data set is still an ongoing project. Here you have the data collected for different kind of liquids, magmas. There are some small variations that probably mean something, but the largest variation observed is among the peridotites, which is probably because tin is incompatible, and so the isotopic effect will be recorded in the leftover the partial melting, which are the peridotites. And I will focus on this data later to try to interpret this in terms of structural and chemical processes. So to make it short, why are iron and tin interesting for planetary science? Well, because we can test a lot of fundamental hypotheses concerning the processes involved in the formation of planets, from the evaporation, what happens during giant impacts or during nebular condensation or partial vaporization for tin especially, but also for iron. What happens during metal silicate partitioning? Can we tell something about the composition of the core or the processes involved during the core formation based on these isotopic systems? And also, can we have some information about the processes involved during melting on Earth, and are we able to find a probe of the particular oxidizing state of the Earth as compared to other bodies? So now I should focus a little bit on the structural and chemical properties of these elements. I will not focus on iron because I could spend days on that. I will just, and I guess most of you have some clues about the chemistry of iron, the valence state, the coordination numbers. So I will talk a little bit about that when I present my results. But I figured out that maybe you were less used to the properties of tin. So here is a quick overview of the structural and geochemical properties of tin. This is the log gamma Kd metal silicate of tin as a function of the oxygen fugacity. And as you can see, there is a very, very strong effect of the redox conditions on the tin solubility. There are a couple of studies, maybe a few tens of studies dedicated to the behavior of tin in magmas. Most of them have been published in the 80s in Russian journals. So it's not that easy to have access to this data, but now Google does amazing things. So these are a few data. This is also something interesting. So tin is chalcophile, which means that it's highly sensitive to the sulfur contents. So there is something like a 3 orders of magnitude difference when you add sulfur into your system. But based on these studies in the late 90s, it appears that increasing the pressure by a few GPa, I'm not talking about what happens at very high pressure, but increasing the pressure at up to few GPa doesn't change much the partitioning of tin. Here I'm just talking about the properties of tin as an element, not as the isotopic system. Something that is also very interesting for tin is that the properties like the diffusion coefficient changes a lot as a function of the oxygen fugacity. And it seems, based on the few data available so far, that the change is pretty steep, which means that we may, if we had a good calibration of this curve, we may be able to probe the redox state of the mantle in a much more accurate way than what we are doing these days with iron, because the change between 2+ and 3+ in iron is really sluggish and not that easy to constrain. And based on this data, looks like around QFM, the transition is around QFM and is pretty narrow. So it has to be refined, and there are some people, at least in Europe, working on this calibration. But it's something that is really promising also with tin. And finally, tin solubility is highly sensitive to the melt composition and the local environment of tin. You can see this on this figure with the solubility of tin being presented as a function of the oxygen fugacity for different melts. And as you can see, when you change the ratio aluminum versus sodium and potassium, the solubility in oxidizing conditions varies by an order of magnitude or so. And so it's a huge change as a function of the composition of the melt. So why is it interesting to look at the chemical properties and structural properties of these elements before turning to the isotopic aspect of the story? It's because actually when we deal with partitioning of isotopes, we are just dealing with some kind of chemical reaction. So these are some basics on isotope fractionation, first based on, or as seen by the physicist, and then as seen as by the analytical geochemist. So if we want to start in a very simple way, you can see the isotopic fractionation as the distribution or the substitution of an isotopic element of an isotopes by the other. And so you can write this kind of equation where the compound A containing n atom of X, C its atoms X substituted by the n X star atoms. And so there is some kind of equilibrium. And this equilibrium is described by a reaction constant. So the reaction constant, as for any kind of chemical reaction, can be written like this, with one exception is that we are not using the Gibbs free energy, but the Helmholtz free energy, just because during the isotopic substitution, the volume doesn't change because the atoms are more or less the same. So this is not true for hydrogen, for instance. But for tin and iron, at least, it's perfectly true. And so we don't need to deal with the Gibbs free energy, but only with the Helmholtz free energy. And this is quite interesting because F, if we move from the thermochemistry or macroscopic thermochemistry to the statistical physics, then F is directly related to the Z function that we call the partition function. And this partition function has many, many properties. I'm not going to go into too many details, but it can be factorized into 3 terms: rotational, translational, and vibrational contributions. And it's easy to show that as far as isotopes are concerned, the rotational and the translational contribution can be skipped. We can talk about that later if you're interested in. So basically, if we are able to calculate or to measure the partition function, the vibrational contribution of the partition function, then we are able to calculate the equilibrium constant and then to predict the fractionation of isotopes. And this is something that we can do. So having this formalism exposed, then we can move to what the geochemists use. We call that the reduced partition function ratios or the beta functions. As you can see, the way we write it is just the way we could write an equilibrium constant. And this, because it's only a function of Z, it can be calculated. And it can be calculated if we know the vibrational partition, the partition function for the vibrational states and the density of state of the material. And so that's the key here from the spectroscopic or the theoretical point of view, is to have access to this G in order to calculate the beta functions for each mineral. And then we can bridge the gap between this physics and the analytical geochemistry. So from the geochemist point of view, what we measure in with the mass spec is the delta, is the deviation of the isotopic ratio of mass 1 and 2 against a reference. And it is expressed as the deviation regarding this reference. So this is what we measure with the lab spec, with the mass spec. And if we have coexisting minerals, say minerals A and B, coexisting in the rock, and we assume that there is some thermochemical equilibrium, then the difference in isotopic signature measured in 2 different minerals will give you the fractionation factor. But the fractionation factor can also be derived if we know the beta functions for A and B. And so that's where physics and geochemists meet, just because what we need to interpret the isotopic results collected on rocks is this alpha factor, and this can be derived by theory or by spectroscopic methods or by analyzing the samples. So I'm done with the introduction. Now let's move to experimental results. So the first thing that people have been doing in the early 2000s was to try to adapt the experimental petrology design to this kind of question. So that's something that I've done. That's something that Anat has been doing for a few years now. And there are actually an increasing number of people worldwide trying to adapt this, this experimental design to the isotope geochemistry. I will not talk too much about that today, but I will just try to explain why I'm not going to talk about this. The big issue with this kind of experiments is that we are looking at variations that are on the order of 0.1 per mil. So when we look at equilibrium for isotopes, we are looking at equilibrium conditions that are really drastic. That makes the experiments always a bit tricky, and the results always, I mean, how do you say that? Well, it's always open to interpretation. So these are two examples of what can happen in a capsule. So these are experiments that we've been doing with Bjorn some time ago. I think it was the last time that I visited Bjorn here in GL. The idea was to run diffusion experiments in different conditions with iron as oxidized iron and reduced iron in diopside melt, look at the diffusion, derive the diffusion coefficients that are indeed different between iron 2+ and 3+, and then to look at what happens to isotopes. And what you can see here is that the fractionation that you induce by looking at this kind of diffusion process is, I say, 20 times what you want to resolve on Earth. It's even worse if you move into the Sora effect. So this is a study by the Chicago group, and this is the kind of fractionation that you observe for magnesium and iron when you have some temperature gradient. And as you can see, if you have 10 to 50 degrees variation into your system, then you have, again, the fractionation that can be several orders of magnitude higher than what you want to resolve experimentally. So it's always really complicated and tricky to run experiments that are convincing for the entire community. This is also quite interesting because actually we can do something with that. This is a study that has been initiated by Corliss, Mathieu, that you know here pretty well. So this is an olivine crystal that has been found in the lava lake in Hawaii. As you can see, there is some zoning, and this zoning is clearly seen here as the forsterite content of the crystals. But what is interesting is that when you see this sample, it's always a bit tricky to tell if it's a secondary process which involves actually diffusion or if it's related to the continuous growth of olivine in a magma chamber. So of course, on this lava lake, it's pretty easy to tell. But if you imagine that you have just a piece of rock coming from outer space and you have no idea of the geological history of this rock, then it's quite complicated to know if it's primary or secondary. With isotopes, it's really easy because the lightest isotopes runs faster. And so if you see this kind of profile with magnesium moving out and iron moving in with the associated fractionation of isotopes, then you can tell that, yeah, this is just something, this is secondary. This is related to the re-equilibration of your rock because it's a xenolith. Okay? And that's something that is really important if you look, if you think about Martian meteorites where the magma, the geological context is not very well known. Anyway, my point is that conventional high pressure and high temperature experiments, they are crucial for most of the systems like calcium or silicon or magnesium. There's no choice. We have to address these isotopic systems using these experiments, but they are always controversial. And you have to be prepared to argue forever about the results of your lab against the result of other labs. For iron and tin, we are a bit more lucky because there's a way to get everybody happy. The way is to forget about these high pressure, high temperature petrology experiments and to move to a spectroscopic approach. And that's something that works very well for these two isotopes because there is a very special spectroscopy that we call NRIX that actually can provide the information required to derive the beta functions and then to predict the fractionation factors. So all the experiments, all the results that I will show you in a few minutes have been collected at APS on sector 3 and sector 30, which are two beamlines. The first one is dedicated mostly to iron and dysprosium and europium, and the second one, sector 30, is only dedicated to tin. The spectroscopy is interesting. It's a time result spectroscopy, which means that we will collect only the nuclear decay, the nuclear scattering, and we are able to filter and to get rid of the electronic scattering resulting from the excitation of the atoms. It relies on the fact that there are excitation on the excitation of the low-lying nuclear excited states for 57 iron and 119. So basically, this spectroscopy shares some aspects with the Mossbauer spectroscopy, and that's the reason why I'm interested in tin and iron. It's the two most important or famous Mossbauer elements. These two beamlines, sector 3 and sector 30, are also able to collect synchrotron Mossbauer spectra. So this is really a spectroscopy that is related to maybe something that you are more used to deal with. So what do we collect? We collect phonon excitation probability density function that we call also scattering probability. And this is the kind of spectrum that we collect with the resonance here. So that's the elastic resonance associated with the fact that you send an X-ray with the exact energy required to excite the low-lying nuclear state, and then you observe the elastic decay of this excitation. But what you can do here, and it's more or less what we do also with conventional Mossbauer, when you move a little bit the source, then you can change a little bit the energy around the resonance peak. And in that case, you can probe the phonon density of state. Here, if you provide a little bit more energy than what is required to observe this resonance, then the extra energy goes into the excitation of normal vibration modes of the tin sublattice. And you observe what we call the phonon creation. And on the other side of the relay, you have the opposite phenomenon where the vibration modes of the sublattice provides the extra energy necessary to observe the resonance. And that's what we call the phonon annihilation. So from this spectrum, so what is interesting here is that we can perform experiments in situ at high pressure in a DAC cell, in a DAC, for instance, at high temperature also. We have performed experiments close to the glass transition temperature to probe the possible anharmonicity of the signature of glasses, for instance. We don't need any chemical equilibrium because actually what we are doing here is to probe the vibrational properties of a single phase. And having the properties of each interesting phase, then we can combine mathematically the results to provide the fractionation factor. So we don't care about equilibrium fractionation related to diffusion or thermal gradients. And one good reason for that also is that we are working with pure tin 119 or pure 57 ion. So the isotopic fractionation when you have a monoatomic sample is pointless. From this scattering function, we can derive a number of important properties. The most famous one is the partial projected phonon density of states of the tin or the iron sublattice, because this spectroscopy only probes the local environment around the Mossbauer nuclei. We can derive the Debye sound velocity, which is something that has been used by geophysicists for quite some time now. So but in this case, we are just interested in this part of the spectrum. And we can derive vibrational properties like vibrational entropy and so on. But what is interesting for us is either the average kinetic energy, which is the second order moment of the scattering probability, or the mean force constant, which is the third order moment of the scattering. Why? Because if you have access to this force constant, which is force constant of the bond of your elements with the first neighbor, then you can calculate the beta function as a very easy function of the force constant. So if you have a way to calculate this force constant or to measure this force constant, then you have directly access to beta. So that's something that we've been doing. So the first thing that we've been doing a few years ago was to test the sensitivity and the robustness of the method. So these are the PDOS of iron-bearing oxides. As you can see, everything looks nice, and it's a little bit noisy here, but nothing too bad. But what is bad is actually that since we are looking at the third order moment, then the energy here is the square or the cube. And then, as you can see, the little bit of noise that you can have here at the tail of the energy spectrum becomes really bad. And then if you take the integral of this signal, you can see that the force constant never converges, which is a big issue because you don't know where you have to cut the integration. It's like, is it noise or is it signal? And it's not that trivial. So that means that we need days and days and days of data collection to have spectrum that are good enough to do geochemistry, which is not the case when you're doing geophysics because you are only interested in this part of the spectrum, which is collected very easily. So here you have 3 examples. 2 of them are good. You have a plateau, which means that the integral of this converges, and you are just integrating noise if you increase the energy limit. But in the case of Goethite, it's a little bit more complicated. Then we compare the results with experimental data available. So the red line is what we predict based on the spectroscopy, and the black dots are data collected by Anat when she was in PhD, I think, on the magnetite firelight system. And as you can say, if we disagree sometime on the results of experimental petrology experiments, at least here we totally agree, which is good. This is another example here with the clinopyroxenes. And this is the agreement between what we measure and what is predicted from DFT calculation. So these are 2 examples with GGA and GGA plus U. Don't ask me exactly the details of that. The calculation has been done by Marc Blanchard. And what is interesting is that if you use this GGA plus U, the agreement with the experimental spectra is pretty good, and the fractionation predicted, so the beta function predicted and measured are also very close, in close agreement, which means that this method actually really works to predict iron isotope fractionation. So this is one of the first results that has been published by Veniamin Polyakov in Science, and he was using available data on postperovskite and bridgemanite to claim that maybe there could be a huge pressure effect. As you can see, all these lines are close to 0, but in the case of postperovskite, there was a huge isotopic effect to be predicted, and then it was sustaining the idea, supporting the idea that maybe the signature of the Earth was related to the size of the Earth. The big issue with that is the data that were collected on the bridgemanite were dedicated to a study of sound velocity, of seismic properties. So the data were collected to be optimized in this area, where the geochemists that we are interested in this area. And this is just too noisy to be used as a starting data set to predict the isotope fractionation. So this motivated my group with Nicolas Dauphas and Anat with Wendy Mao to perform measurements specially dedicated to the iron isotopes. So these are the data collected by Anat. And so in itself, what she shows here is that the pressure has an effect on the beta function, which is not surprising, just tells you that with pressure, the bonds are stiffer. But what is interesting is that the way the bonds become stiffer are different for the different metallic alloys. And so potentially, this could tell you something about the fractionation that you would expect as a function of the light element present in the core. So that was a pretty nice story. At the same time, but we are a bit slow, we were collecting the same kind of data with the group of Afulin on different alloys, including the binary iron silicon, iron nickel, iron sulfur, and ternary alloys like iron, nickel, and silicon. And we also collected data on basalt classes. So these are the data collected in terms of force constant here. So as you can see, the force constant increases. We see something interesting here for the basalts, which is probably related to the change in the coordination of silicon around 30 GPa. So changing the coordination from 4-fold to 6-fold in the silicon of the basalt affects the force constant of iron. But when we combine all these data and we try to predict the effect of the metal silicate segregation in the high pressure and temperature condition of core formation, we end up with the idea that actually there shouldn't be any kind of signature preserved because the temperature is just too high. So this is a conclusion that was we agreed on this point with Anat, more or less. We went a little bit further and looked at what happened to bridgemanite and ferropericlase when we increased pressure. And what was interesting here, again, the force constant is plotted against pressure, is that we are able to show that the spin transition had a very strong effect. As you can see here on the ferropericlase, when the spin transition occurs, then the force constant increases a lot. Nothing like this has been measured on bridgemanite. I'm not sure about the drop, but at least there is a plateau for the bridgemanite that happens more or less when iron changes a little bit. I mean, the SMS spectrum of the bridgemanite changes a little bit around this pressure. Interpretation is not that clear, and clearly there's a need for more data on this mineral. What is important is that the fractionation that could be predicted based on this spin transition effect is huge. But then comes the problem, the geochemical problem, is even if you fractionate the isotopes between ferropericlase and bridgemanite, how are you moving from what happens between two minerals settled in the lower mantle? How do you move from that to a planetary signature? Is there any process like partial melting or something that could make this signature rising up to the surface and then be measured by mass spec? And the answer is apparently no. No. So we modeled the crystallization of basalt magma oceans, and we were not able to see any significant fractionation of iron isotopes, even though the force constants are very, very different here due to this spin transition. Moving rapidly now to the magmatic context, we've done the same kind of study on spinel as a function of the redox state this time. So here you have the ferric-ferrous ratio plotted here and here, and the force constant. As you can see, there's a huge effect of the redox state with iron 3+ driving heavy isotopes concentration in the phase. This is something that we see for different kind of melts, and this is something that we also observe for different spinels. What is also interesting here is that there is a significant difference between the rhyolite on one end and the basalt, the andesite, and the dacite on the other end. So I will talk about this in a few minutes. So when we found this results, we were very excited, and we say, okay, so we are going to explain this signature just because, well, the morbs are very oxidized, and if we take something like 15% iron 3+ in the morbs, as compared to the source that is essentially made of iron 2+, then we should be explaining the signature. But it turns out that, nah, it doesn't work like this. The effect is not strong enough. The direction is good, but we explain something like 1/3 of the fractionation. So clearly the redox effect associated to the melting of morbs and the generation of slightly oxidized melts is not going to does not explain this signature. But we can explain this signature, and this is related to the formation of oxides at the very end of the crystallization. But this is mainly due to the fact that moving from 45 to 75% silicon, you move from something that is basaltic to something that is rhyolitic. And as I just mentioned before, there is a strong effect of the composition and the structure of the melt that makes rhyolites lying away from the main trend defined by regular basalts. And so we wanted to understand what was the structural or chemical parameter that actually affects the partitioning of isotopes, especially in the reduced melt. So to do that, I went back to what I was doing with Bjorn in 2004. So I moved to very, very simple glasses, potassium silicone, potassium silicates, sodium silicate, and calcium magnesium silicates. So these are the data collected for calcium magnesium silicates, which are very close to basalts in terms of structure, containing iron, of course. And they lie, for the reduced and the oxidized one, exactly with the basalts. So no big surprise. But when you you prepare glasses with a lot of sodium or a lot of potassium, then you see the constant that increases, and actually the potassium glasses lies exactly where the rhyolite is. So what it tells you is that there is a very, very strong compositional effect on the fractionation of isotopes, especially when the alkali is huge because of the size of potassium. The iron 2+ is probably tends to be in 4-fold coordination instead of 5-ish, 6-ish fold coordination. And because of that, the bond strength and the force constant increases. And so this is a direct manifestation of the effect of the composition and the changes in the local geometry of iron on the iron isotope fractionation. We now move 5 minutes, a bit late, on tin. So these are the results. All these data have not been published yet. They are under review. So these are the different samples that we studied containing tin. So a lot of different alloys with different constant tin content, containing nickel or no nickel. We also studied silicate glacis, so rhyolite, basalt, and statite, and anorthite, and sulfite. So these are the typical spectrum collected for SNO and SNO2 oxides. And as you can see, we are very good now also in predicting the dose. The data are the grayish, bold spectrum, a little bit noisy spectrum here. And the models performed by the DFT calculation performed by Marc Blanchard are the thin blue lines. And as you can see, except a little shift in energy toward lower energy, the prediction is excellent. Even the modes at high energy in the 80 millieV are measured by Henriks and are actually predicted by DFT calculations. So here are now the spectrum that we collected. So this is the signature of tin in iron nickel and pure iron metallic phase, so there is no big difference here. These are the data for the metal phase. These are the data for the silicates. What is interesting here is that you can directly tell that there is a huge effect of the redox state. So the blue and the green, they are reduced tin 2 plus bearing silicates. These ones are tin 4 plus bearing silicates. And there is also a very strong effect of the composition of the melt, especially here for basalts prepared in air, so the oxidized one and the rhyolite. Everything is different, including the sound velocity, the bulk modulus, everything is different. And also something that is interesting is that there's no doubt on the fact that tin is dissolved in the glass and is not present as precipitates, just because look at the smooth and broad signature as compared as what we collected on the pure oxide. So there's no doubt about the fact that we are not looking at precipitates. So these are the data. I didn't plot what we measured on the metal phase for now, because I still need to understand exactly what we have. But here you have an effect that is much, much stronger than what was measured for iron, between 2 plus tin and 4 plus tin. The force constant increased by a factor of 2. And there is a huge compositional effect also. Here you see the anorthite, and the anorthite has a force constant that is very, very low as compared to the other silicates. And this may remind you the fact that the speciation and the coordination chemistry of tin is highly dependent on the aluminum content of the glass. And the fact that there is a huge effect on this anorthite is quite coherent with what we know of the chemistry of tin. And it's also very interesting to interpret the data, say, for instance, on anorthosite or in very aluminum-rich magmas in extraterrestrial rocks. There's also a huge effect of the composition here between the rhyolite and basalts, for instance. And this can be rationalized in terms of fractionation, prediction of the fractionation as a function of temperature. And so these are the preliminary conclusions that we have. The first thing that we have seen, or we seem to observe, is that the metal silicates is not recorded by tin isotopes. Like even at low temperature, there's no strong difference between the force constant of tin in an iron matrix and as compared to what is found in tin 2 plus glasses. But there's a huge difference between tin 2 plus and tin 4 plus bearing glasses. So definitely the stability of tin 4 plus in magmas and minerals would induce a very large isotope fractionation. And the composition dependence is also very large, and so could also explain some signatures in the granitoids and all these, basically where we find a lot of tin. In terms of interpretation, so I remind you the kind of data that were collected so far. So there is a small variability of the isotopic composition of tin between the different liquids or magmas, but there is a large variability in granites and in peridotites. So the granites, it can be related to the aluminum content of this kind of liquids. But what is also very interesting is if you look into more details about this peridotite and you plot this data, the isotopic data, as a function of the scandium, which tells you a little bit about the partial melting, what you observe is that when you lose your clinopyroxene, then you change drastically the isotopic composition. And that's very interesting because in the mantle, where are you going to accommodate tin 4 plus? Well, actually, the only place where you can put tin 4 plus is actually in clinopyroxenes. So the variation that we observe in peridotites here tells you that it's is related, to the presence of tin 4 plus in the peridotite before the melting. So we have here some keys to better understand what's going on in terms of phenomenology of tin isotope fractionation. And this is the last slide that I want to show you is a modeling of the fractionation of the isotopic signature of tin as a function of the degree of melting in morbs and in the corresponding peridotites. And as you can see, we can reproduce all the data, including this very depleted peridotite, just taking into account this 2+, 4+ fractionation that we have been able to measure using the NRIX. So we are actually really providing some robust interpretation to this few data available, and I just hope that geochemists will now focus a little bit more on tin. So the messages, the conclusions. So pressure has an effect on the beta functions, but as far as we can tell, the manifestation in geophysical context may be more than subtle. That's my point of view. We can discuss about that. The high pressure mineralogy also has a very strong effect on the isotope signature, but the way you can produce observable almost at the surface of the Earth is not that easy in this case. So how do we need to find a process that is able to segregate ferropericlase from bridgemanite, for instance, at some point. And what is clear is that the redox and the structural effects have very strong effect on the iron and tin isotopes partition. Two questions. Well, first, the good thing is that the non-traditional isotopes may be quantitatively used to model the crystal and the mantle differentiation. It's not so clear to me if we can say something, tell something about the core mantle differentiation so far. But what is still a bit complicated to understand for making prediction is the entanglement of the redox and the coordination chemistry. And that's something that is very tricky because when I say something about the iron 2+, iron 3+, and the effect of iron 3+, I'm not sure that I'm talking about valence or if I'm talking about coordination chemistry, because iron 3+ is not coordinated the same way as iron 2+. So that's something that we are still working on to try to disentangle this, because if we are able to understand in more details what happens with the coordination chemistry, then these results could be extrapolated to systems that we cannot probe with these NRIX, like silicon, calcium, magnesium, because if the isotopic fractionation is only related to the coordination chemistry, knowing the structure of melts and minerals is maybe just enough to predict any kind of fractionation. So that's the goal. And I will thank you for your, I've been a bit long, so I thank you for your attention. And I want to thank here all my collaborators. First of all, Nicolas Dauphas. I've been working with him on this project on the iron project for 10 years or so. And all these nice people at APS who have been supporting us and invited us to work with them. In 2008 or 9, it wasn't that easy to convince people at APS that it was very interesting to look at iron isotopes using this kind of spectroscopy. So that's that's because of their help and the enthusiasm of Ercan Alp that we were able to open this field. Thank you. We didn't. We didn't because, so I totally agree with you. The only thing is, since even taking the the most extreme configuration, which is the one that I show you here. Even if we consider this extreme and abrupt transition, we are not able to produce any significant effect in the upper mantle. Okay, even any kind of fractional crystallization of the lower mantle is not, the anomaly that is produced is not transmitted to the upper mantle and so to the bulk Earth. So since the result is negative, we didn't pay too much attention to this problem because it would make the whole thing even more sluggish and more subtle. So if it doesn't work at the 0 order, it's not going to work in the second or third order. So we didn't go into too many details on that. An harmonicity is, I mean, it's always the kind of question of like tricky or nasty question that you ask in this kind of study. The only thing that I can tell you is that an harmonicity should decrease. In principle, I think it should decrease all these kind of effects, so make everything less extreme in terms of dependence regarding pressure or regarding temperature. We tried to test this collecting data on glasses from nitrogen temperature, liquid nitrogen temperature, using also an heating stage to 800, 900 degrees for days. Sector 3. Yeah. That was not the problem. The problem is the beryllium window. We killed 2 APDs during this experiment. So we decided that it was good enough. And so to make it short, over this 5, 6, well, maybe 800 degrees, we are not able to see any kind of an harmonicity. But we are still working on solids. That's something that is a bit tricky, and we need to understand is that this spectroscopy only works with solids because you need to have a recoilless phenomenon. So we cannot probe liquids. And so all these results are based on the assumptions that basaltic glass is like magma, that molten iron is like solid iron, and so on. So that's something that may be a bit tricky, a bit different. That's something we need to work, but I think the only way to go is ab initio calculation for that, because the spectroscopy is just not doable in the liquid state. Yes. Yes. So that's yeah. So, well, they are modern peridotites. So this data compilation includes also peridotites that have been potentially metasomatized. And so so that's the reason why they are not exactly the same as the other ones. So this one, there are more data, but some of them, they may have seen some fluids. That could be, yeah. That's exactly what you expect, right? If you see that, you say just one is positive, the other one is negative, everything's fine. No. No. Dysprosium, European.
Other isotopes of
Ah, no. No, only 1119 and 57 ion. Yeah. Yeah. Actually, something like 10 was boron. Like all the Mendeleev table included like 10 atoms that makes resonance. Lunar data. There is some lunar data. I cannot show them because it's not mine. They are not mine. Yeah, so you have to ask Caroline Fitoussi. They have been working on that. They have some data on different petrology, and it moves a lot, as you can get. But it's not that clear if it's related to vaporization, sputtering of the surface of the moon, or if it's completely related to magmatism. So they are working on that, but I'm not involved. That's what we wanted to show initially. I think that for iron is going to be complicated to really disentangle the redox and the coordination effects. Okay, because and the valence chemistry of iron is really complicated. Just consider that FeO and Fe2O3, they are never stoichiometric, and if you pressurize this, you have like weird charge transfer. So I don't see how we will be able to really disentangle these two effects. Yeah, but for the, that's the problem of this kind of science. I mean, if you want to do something on the compositional effects, you need a lot of beam time, and it takes forever to take. I mean, there's nothing as boring as collecting an Henrik's spectrum for geochemistry. It takes. Yeah, so morb is fine. I mean, we have the data for morbs. Any kind of redox. You tell me which redox you want, I give you the fractionation regarding olivine or pyroxene. So that's done. No, it doesn't. It's a good direction, though. So that's something that is interesting. I mean, it could be the opposite direction as it's. It could be, or it could be different cycle. I mean, if you run some distillation, then you increase a little bit the fractionation. So if you just imagine that you have partial melting, recrystallization, then partial melting, recrystallization, and you can improve a little bit the thing. But there's no very, I mean, you can always play with models. There's no very completely convincing, simple, and elegant way to explain this. Another aspect that I didn't mention at all is the fact that some fractionation during nebular and during accretion of planets may have occurred also. So there is three hypotheses actually to try to understand this signature. The first one is pressure. I don't trust it. Redox controlled partial melting. I think it has an effect, but I don't know if it's the order of magnitude is large enough. And there is vaporization. So for tin, it's crucial, but for iron, it's possible too. I mean, there has been some experiments showing that you lose iron in high temperature and during giant impacts and these things. You lose iron, you have a vapor. In that case, you will fractionate isotope very, very badly. So it's not excluded that maybe we are looking at some signature of the giant impacts that we don't have on Mars, for instance.